Welcome back to Thermodynamics 1, ME236. This is Class 2, and we're moving on to Section 1.8, which is just sort of like a short preview of energy. It's one of the biggest topics, most important topics in thermodynamics, and we're just going to talk about it a little bit so that we get prepared to learn more later. So this comes up in several chapters as we approach, but Chapter 4 has some of this in here. So let me just talk about it a little bit. We already kind of have sort of a big idea just from life and physics classes that you've taken what energy is. It's really what engineers deal with a lot in terms of trying, analyzing, and looking for ways to change energy from one form into another to solve problems. A lot of that problems might be making a ship go through the water, making a car go fast, generating electricity for homes, power within a factory, power in a jet aircraft to take off, all of the changing from one form of energy into another, and many different forms. So we want to try to put together some definitions of different sorts of energy and types of energy, and then we're going to, in order to calculate for a purpose, we're going to see that we have a useful tool in the specific energy. So we just talk about energy in a global sense. We have internal energy, which is a bunch of molecules kicking around inside of something. I have kinetic energy, so that's actually the motion of the big thing that we're looking at, right? So this is very microscopic right here, and then we're taking a macroscopic look at that microscopic action. We have the kinetic energy, so that's often is 1/2 mv squared is what we want to associate with the kinetic energy, and we have potential energy. There's lots of kinds of potential energy, but the one we mostly care about is going to be gravitational potential energy, and that's really about how high you've risen something, right? If you take something that's on the ground and you lift it up, you've increased its potential energy. You let go, that potential energy turns into kinetic energy. And we will look at this in dynamics and in fluid mechanics a whole lot. It's really important. But for now, let's just say that we have these types of energies, and we have the total energy E. Well, for us, because this is, if we were to cut the mass in half, you would be cutting this energy in half, and that would be an extensive property. I think I have that right. And we would like to have an intensive property. So quite often what we do is we divide by mass. Not necessarily mass flow rate. By the way, I think that's incorrect to say mass flow rate. I wrote that, and I should take it out. Let's see. No. Not mass flow rate. Not mass flow rate, but by the mass. There is often what we'll do is we will multiply a mass flow rate by this specific energy, and then we get like an energy flow, right? Energy. Then we get our energy rate. For instance, work. If you do the rate of work is power, right? So if you have the specific energy difference between two states, and we multiply it by the mass flow, we could get the power that way. All right. So just be aware that dividing it by the mass is a useful thing, and we change from uppercase to lowercase. So get used to that. So you can see that the kinetic energy is 1/2, not m, because we divided it. See, it's lowercase, so it's 1/2 v squared. And for potential energy, usually that's going to be the weight of something, or mass times gravity times the thing times the distance that it moves in the vertical direction. So that's mass times gravity times the vertical direction. But this is specific energy, so we divide by mass. So you can kind of see where those things come from. And they're also bringing up this thing called internal energy, this U right here that you see that was a capital U, now it's little u. And that's broken down into, here they're saying external molecule. I don't know what they mean by that. And translation of the molecules, and then internal molecule. So exterior molecule stuff, internal. I don't quite understand what they're talking about right there. But anyway, they're saying that this internal one is broken down to the individual molecular potential, rotational energy, vibrational energy, atoms, all of that stuff. You don't need to know what these things are, but just get a sense that this internal energy has a lot of energy parts to it on a micro scale, and we're looking at the macro scale. And then I decided to put this in here. This is often called, or one of my colleagues used to call this, the energy equation, right? So the energy accounting equation. And you can see what I was referring to about the mass flow rate up here. The mass flow rate is multiplied by these things. And so you see here's mass flowing in, here's mass flowing out of a system, here's the work that's being doing on the control volume, here's the heat coming into the control volume, and here's the collection of energy the change of energy within the control volume. So because it's a dt of this energy within a control volume. So this is an introduction to the new stuff. I also want to make a notable an appearance of a good buddy of ours. This particular book takes a little while to introduce him, but he's famous, he's great, we love him. It's enthalpy. Enthalpy is great. It's a good parameter to use in many calculations, and it is sort of a combination of the internal energy and the flow work. So it's kind of so right here is that H as they're showing in there, and a lot of times that H is going to be the major. It's going to be much larger than these other pieces. Is going to dwarf the gravitational. The velocity change might not be nearly enough to be able to be influenced by this enthalpy. And the enthalpy is internal energy and something called flow work, which we will learn about soon, which is pressure times specific volume. So anyway, this is like a really important introduction to things in energy. We're just talking about it, passing it underneath your nose. You don't need to use it for anything in this homework, but we will be working on it very soon in later chapters. While we're here, let's get a little bit acquainted with the different units that we use. We have energy, E, big E, or little U. We use joules in the SI, right? And a joule is equivalent to 1 Newton meter, and you should memorize that. That should be something that's second nature to you. Don't necessarily need to know this other part, but except that a Newton is a kilogram meter per second squared. So of course a Newton meter is a kilogram meter squared per second squared. That makes kind of sense. Calorie, I don't really think we used it all that much. And by the way, kilocalorie is what your food is. Food is actually measured in kilocalories, so it's even 1,000 times worse than you thought it was. A foot-pound is what often gets used for mechanical work, mechanical energy in the U.S. units. But we have this weird thing called a BTU, and this is a British thermal unit. The British thermal unit is a classic way that engineers in the United States for many decades have been using the British thermal unit, and it's not going away anytime soon. A good conversion to notice is 778 foot-pounds per BTU. So we're going to do a conversion. 778 foot-pounds per BTU is a good conversion scale that I used to use all the time as a engineer and as a student. The heat capacity, we usually use in US units, we use BTUs per pound mass degree Rankine. It's interesting that for the heat capacity is kilojoule per kilogram Kelvin, right? And those are these, you'll often see a C subscript P or a C subscript V. You'll learn what those are very soon. Also, entropy, lowercase s, also has these units, so be aware of their existence. And specific energy, so that's usually, enthalpy is one of these, so we could actually put enthalpy in as one of his brothers right in there. So you have a kilojoule per kilogram is usually what you use in SI, and a BTU per pound mass is what's usually used in the US units, aka English units, I don't know. Power, a watt is It's what we use in SI, which is a joule per second, aka a Newton meter per second. Kilowatts is often what we deal with because it's usually large enough that makes sense. A foot pound, I think. Okay, so I've been saying this wrong for so many years, I can't stop myself. I know they say pound force foot. A foot pound is what often I read on probably the first torque wrench I ever put in my hand. So I will always accidentally put feet before pounds, or foot pound, but I guess it's pound force feet. And that could be a BTU per hour. That's actually a very common thing to do, or BTU per second. Here's the conversion in horsepower to kilowatts. That's also a good one to learn. It's nearly 75%. And then also this guy gets used a lot. Oh, and this guy. These are very, very common conversion factors that I used to have to look up almost every time because I would forget. But I did quasi-memorize them because I was often on the lookout for them when doing calculations. And it's a important thing to memorize a little bit of stuff in this world. Yeah, you could look up a lot of things, but memorizing it, especially when you working through something and all of a sudden you recognize a number that you've used over and over again, you could recognize why it's there, why it exists. And that goes along with the other discussion in the class 1 about units, how you could do a lot with units. You could also recognize with in a particular unit conversion the significance of a particular number that you happen to be running across. So we'll go on and do the next class. Next video. A lot of videos in this class.